All right, welcome everyone for the special colloquium today. So we're very happy to have Allan Sly from Princeton University speaking at the colloquium. For those of you who don't know, Allan is a faculty. So he used to be a faculty at UC Berkeley, and he was my PhD supervisor. But he did his PhD from Berkeley in 2009, and then he was a faculty at Berkeley until 2016, and moved to Princeton thereafter. His long list of awards and accolades include a lot of things, but most recent of which is the MacArthur Fellowship. So we're very happy to have him speak today, and he'll talk about thresholds in recovery of sparse stochastic block models.
Thanks. Okay, is this okay? Yeah. So I'm going to be talking about so really suggested, given the sort of wonderful lectures of Sanjeev Aurora this week, to speak on something sort of statistical, but this will be a topic that has both statistics and also statistical mechanics and sort of connections between the two, and which is a sort of strength of ICTS and it's I should say it's wonderful to be visiting here. It's been a very nice couple of weeks. So the basic problem I'm going to be talking about is community detection in networks. So you have the basic kind of problem is you have some large network, there's some community structure in it, and you see the graph without the labels of who's in which community, and you want to determine who's in which of the communities. At least approximately. And so, so what sort of examples of this are there? So the one that's sort of easiest to describe and think about is social networks. And so you imagine it could be that your different political persuasions mean that you're in different communities. So these days, everything's more polarized. If you're less likely to be friends with someone of the opposite political persuasion, and so you might see this structure in the network. Or it could be other interests. It could be what cricket team you support. These days, in the US, I don't hear much news about cricket so much, but whenever India beats Australia, I am reliably informed of this by my Indian friends and colleagues, which at the moment is happening a lot. Okay, and the story I want to tell today is about sort of connections between this sort of statistical problem and some sort of very interesting sort of math from both mathematical physics and probability theory. So with the Ising and Potts models, spin glasses, random networks, random graphs, random walks-on graphs. Okay, and so the basic model I'm going to look at is called the stochastic block model, which is essentially maybe the simplest example you can give of a network that has some sort of community structure in it. And I'm going to focus on the simplest possible case of it, where you just have two communities and they're sort of symmetric with respect to each other. Okay, so we'll have a graph with n vertices, and there'll be two parameters a and b. And so you start off, we'll just sort of label each of the vertices either blue or green to indicate the two communities, each with probability half. So we'll have equal or almost equal numbers in the two communities. And then, so the network structure is what edges you put in. And we imagine that within the communities, there's a higher density of edges. So we'll connect each pair of vertices with probability a over n independently. But you also maybe have some friends in the opposite community, and so we'll connect those edges with probability b over n. So this is the stochastic block model. The scaling of having a over n and b over n is such that it's a sparse graph. So the average degree of the graph is constant as the number of vertices are going to infinity, which is a sort of very natural assumption in a lot of network models. Okay, so this was originally from studied in the statistics community. I think the first reference is Holland et al. From the early 80s. And there have been literally hundreds of papers on it. This is just like 3 particular references, but so Chatterjee is Shurav Chatterjee, who was here a few weeks ago. There's been a parallel effort in the computer science community with a different name. They call it planted partitions. So there's a series of works for them understanding when you can find the 2 clusters. These 2 communities didn't really talk to each other very much. This is sort of an example of community structure within the community detection community. Okay, so it was pretty small, yeah. And later we'll see some new communities emerging in this topic as well. Another, not from the point of view of community detection, but it's also been studied in combinatorics as examples of inhomogeneous random graphs. So if you take A equals B, then that would just be every edge is sort of there with equal probability. There'd be no community structure, and you would have just the classic Erdos-Renyi random graph, the sort of most important model in random graphs. And so for people in combinatorics, this was kind of a natural generalization of that, or at least part of a bigger family of natural generalizations. And so there was sort of work on studying things like when do you have a giant component in the graph. And finally, if you just look at the fixed network structure and then ask, what's the probability that you see a particular partition in the graph? This is just the Ising model with magnetization 0, conditioned to have magnetization 0. So the reason for the magnetization is because we sort of started off saying that the groups will be of equal size, so you need equal numbers of pluses and minuses, essentially. Okay. So prior to about 2010, most of the work was done in the sort of setting of denser graphs, so where the average degree is tending to infinity with the size of the network. Partly because things are just easier in that setting. So as I said, we'll be interested in the sparse case where A and B are constants. We need A plus B to be at least 2. Otherwise, there'll be all of the connected components of the graph will be really small. And if that's the case, then you can't really hope to say anything about the community structure. So our goal in terms of detection of the community structure is what do we want to achieve? Well, the most modest thing is find a partition of the vertices in which you get at least a half plus epsilon fraction of the nodes labeled correctly. A half would just be randomly guessing. So can you do better than that? That's sort of the minimal requirement for saying that you've done community detection. I say a half plus epsilon, but really this is up to a global sign change because even if I could work out the partition exactly, and I wouldn't know if one half was red and the other half was blue, or the other way around. So it's up to that. Ultimately, we'd like to actually get the best possible correlation. And another thing that particularly statisticians are interested in is can you identify the parameters of the model as well? So find A and B as accurately as possible. Okay, so that's sort of the goal. My interest in this problem started with work by a group of physicists. So this was another community that started looking at these problems, and so Dessel, Krajcala, Moore, and Zedradova. And they looked at it from the point of view of, so these were sort of people who studied spin glass models. And so they came up with sort of very concrete predictions about when you should be able to do community detection. And in particular, using the belief propagation algorithm. So I was meaning to write down the formula for this, but it's sort of a message passing algorithm where on every directed edge ij, you have a message from ij will be given by some function of the other incoming messages, which will be, okay, over j next to I, k next to I, k not equal to j. And these so the Raj, you sort of interpret as saying this is vertex I telling vertex j how likely it think it's a blue vertex, and so in their algorithm you start off with some random initial states and then sort of iterate t and see what happens. Now, where does this algorithm come from? Well, if you were looking at say the Ising model on a tree and wanted to calculate the marginal probabilities, you do that using sort of dynamic programming, and it's essentially exactly these calculations. The stochastic block model is not a tree, but you can still sort of formally apply that algorithm and see what happens. So that's what they do, and their conclusion was that the parameter tau, which is a minus b squared over 2a plus b, is sort of the important threshold in this model. So when tau is less than 1, you can't do better than random chance. There's no way of doing community detection. When tau is greater than 1, belief propagation will work. It will approximately find the clusters, and it will actually do essentially get essentially the optimal recovery. And also with some sort of tweaks of the algorithm, they can estimate what A and B are as well. Okay, so these are physicists who don't typically prove things, but they had some very convincing simulations and very convincing theory. So as a mathematician, that's a very appealing thing for us to try and prove. So over the next few years, we worked on proving as much of this picture as we could. Okay. Oh, I should say, previously, essentially, the only results in the sparse setting were by Kodjo-Glahn, who get sort of the same dependence on A, like with a minus b squared over a plus b, except with an extra log factor and not the right constant. But I mean, this you can see. So why is this sort of the right scaling? Well, the bigger the difference between A and B, the sort of more community structure you have. And when A plus B is bigger, in a sense, there's more edges and there's more noise. So this you can think of, tau you can think of in a sense as a signal to noise ratio in the problem. Okay. So our first result was we could do sort of one side and say when tau is less than or equal to 1, you can't. So the identifiability of the parameters. So it could be that you can, yeah, so one thing, community detection is essentially a harder problem than identifying the parameters of the model. But usually if you can do one, if you can do the community detection, you can also infer the parameters.
But the converse need not be.
Right, and actually so I'll come back to this in like 30 seconds. So initially we could say that, you know, you can't detect the clusters, and actually a stronger result, which was that really you can't even distinguish the stochastic block model from an Erdos-Renyi random graph. So if you have, so the average degree in our stochastic block model is a plus b over 2. If we take an Erdos-Renyi random graph with the same average degree and compare them, the models are what's called mutually contiguous, which basically means that as n tends to infinity, no statistical test is going to be able to distinguish between the two models correctly with probability tending to 1. I mean, it's a bit stronger than that, but that's basically what it says. So really, if the difference between A and B is small enough, then just the graph you get really doesn't have any community structure at all. It looks just the same as a completely random graph. And so then the other result, which at least we could initially show, was that when tau is greater than 1, A and B are identifiable. So at this point we could do that problem, but not do the community detection part at that point. And actually, like the proof of this was done by counting small cycles in the graph and looking at how that compares with say the Erdos-Renyi random graph. This would be a terrible thing to do if you actually had real data, but from a math point of view, the parameters were identifiable and you could actually do it there. So in that sense, that was a substantially easier problem. Okay, so the proof of this result that you can't do community detection is quite simple, and so even for a colloquium talk, I can essentially tell you all the details pretty straightforwardly. So we have, and it will depend on the local structure of the graph. So we have one of the instances of the graph, and if we want to do community detection, we want to take two vertices and be able to, like the basic question is, can you say, are they in the same group or are they in different groups? So you know, all you know is the network structure, but suppose I gave you some additional information. I tell you, so this one and this one were the ones we wanted to say if they're in the same block or not. But suppose I actually tell you what state this one is, and then around this vertex, I take a ball of radius L. Here it's just depth 2, but imagine some large ball. And I tell you the community or the colors on each of the vertices on the boundary of that ball. So that's definitely helping you. You get more information. Okay, so first of all, you can ask, what does the structure of the graph in this ball look like? The vertices that are within distance L of the green one? Well, it looks like a tree, and it looks like what's called a Galton-Watson branching process tree, which is basically a tree where for every vertex, the number of children they have is independent, and it's in this case it's given by a Poisson with mean a plus b over 2. Okay, so that's, now, you might say that, and I would agree with you, that a model of social networks where the local structure of the graph is a tree is maybe not very realistic, because what does locally being a tree mean? It means that if you have two friends, then they're not friends. which is not my experience of things. But, you know, so nonetheless, you know, okay. So first of all, I'm a mathematician, so I don't feel the need to justify the real-world nature of these models, but I think also statisticians just find this sort of a convenient test bed for algorithms on more real sort of models, even if things like the local structure might not really reflect what's seen in real networks. Okay, so just to summarize, we have the local structure is a tree, and we're told what the values on the leaves of the tree are. Okay, so what does the distribution of the colors on the tree look like? Well, you can describe it in terms of a certain broadcast process. The root will just be equally likely to be red and blue. And then it can, for some parameter epsilon, as you go from one level to the next, each child will have the same color as its parent with probability 1 minus epsilon, and it will flip the color with probability epsilon. So you just sort of can continue this process down the tree. Along any ray in the tree, it just looks like a very simple two-state Markov chain. Okay. Okay, this model is nothing. It is exactly the Ising model on the tree with free boundary condition. So where there's some formula that relates sort of epsilon to the inverse temperature. Now you may be more familiar with the Ising model on sort of lattices, but which has of course been where the most focus is, but there are also you know, many things known about the Ising model on trees, which is in this case what we need to know. And so what's the question? So what would be the relevant question? We want to say, okay, I tell you the states at the leaves. How well can you guess the state at the root? And in particular, how does your guess go as the depth L is tending to infinity? And so, you know, you could imagine two things happen. One is that the probability that you guess the root correctly will tend to a half. That means there's sort of no information in the limit. Alternatively, it could be that it's bounded away from a half and sort of even as you go arbitrarily deep into the tree. This is equivalent to the question of, is the free measure extremal in the space of Gibbs measures for the Ising model on this, the infinite branching process tree? And it turns out the answer to that's known. So Evans, Kenyon, Perez, and Schulman gave the following condition that 1 minus 2 epsilon squared times d bigger than 1, then you can, then even sort of as L tends to infinity, you still have information remaining about the root, and otherwise you don't. This is sometimes called the Keston-Stigum bound. This is based on a result of Keston-Stigum in terms of understanding sort of multi-type branching processes. The 1 minus 2 epsilon here comes from, if you look at, so we said if we look at one particular ray on the tree, then the states are doing just a simple Markov chain, and 1 minus 2 epsilon is just the second eigenvalue of that Markov chain. And if you want to generalize this to sort of other models, maybe with more than 2 states or you know, asymmetric relations between the two, then the general sort of Keston-Stigum bound is second eigenvalue squared times d greater than 1. So we'll come back to that later. Like the average branching rate, yeah. So the mean number of offspring, yeah, exactly. So it will be like a Poisson with mean d in this case, and And so D will just be A plus B over 2, the average degree. And the flip probability is, well, that's sort of just the probability. Okay, you take a friend at random, what's the probability that they're in the other group? That you can check is just B over A plus B. So if you plug that in, this formula you get exactly tau. And so if tau is less than or equal to 1, even when I give you this extra information of what are the values on the leaves of this ball, you still can't do the reconstruction. And this is using sort of the Markov random field property of this measure. I'm cheating slightly in one spot, which is that, okay, if you look at say the Ising model or a spin system like that, the only sort of interactions you have between the spins come from sort of the edges between them. Here, like the absence of an edge between two vertices also gives you a little bit of information. It means that, if I don't have an edge with someone, it means they're slightly more likely to be in the other group. But you can show that this is sort of essentially negligible. Okay, so that's on the sort of tau less than 1, you can't do reconstruction side. The next sort of developments were, so what happens when tau is greater than 1? And so after that, we found an algorithm that's based on a sort of spectral algorithm that finds an approximate reconstruction of the clusters. So has a 1 plus a half plus epsilon fraction of the vertices correct, and has a running time that's sort of close to linear. And independently at the same time, Mossel-Neeman found a different algorithm, pretty similar, getting the same results. So there. Now, I'm not going to tell you what either algorithm is because I want to tell you what the sort of, because both of these, all of these, our group and Mossel-Neeman are all sort of mathematicians, or I guess he's maybe a theoretical computer scientist as well. So we wrote sort of algorithms to be easy to prove things about, which are not the ones that you'd actually ever want to use. You just sort of have to add in lots of bells and whistles in order to make the analysis of the proof go through. But they're really perturbations of another algorithm I'll tell you, which is sort of the right thing to do. As a consequence of this, it's sort of easy to show that you can estimate the parameters with sort of the optimal rate that you'd want. And then in another work, we said, okay, suppose we can do this weak recovery problem, get some sort of correlation with the right partition. If we take that and then run the belief propagation algorithms for sort of a large number of rounds, we can show that this actually gives the sort of asymptotically the optimal recovery of the partition. Except we can only show this when the signal-to-noise ratio is sort of good enough. There's a specific conjecture which just involves looking at this just this tree model. And if you can solve that conjecture, you can extend this to all tau greater than 1. So it's really there's really just a very concrete math problem that is missing here, which was easier if the signal-to-noise ratio was better. Okay, so next what I want to tell you about are sort of spectral algorithms. It's the basic spectral algorithm. You have a matrix, you look at the eigenvalues and try and, or the eigenvectors and try and recover based on that. So the natural sort of thing that you would first try and do is you take the graph, and then you want to build some matrix out of that. The simplest way of doing that would be, say, the adjacency matrix, which is just aij equals 1 if there's an edge between node I and node j. Other matrices you could build would be the transition matrix of the random walk on the graph, or the graph Laplacian. And so how would a sort of standard spectral algorithm work? You build this matrix, you look at the biggest few or the eigenvectors associated with the biggest few eigenvalues, that sort of projects things to some low-dimensional space, and then you do some sort of low-dimensional clustering algorithm of that. And hopefully that, gives you a good approximation of the partition. So each of these are sort of n by n self-adjoint matrices. And for each of these matrices, spectral clustering doesn't work well at all. It's sort of you get very little sort of correlation with the right partition. And what's the problem? The problem is specific that the eigen vectors are picking up on the wrong sort of properties of the graph. So if you take the adjacency matrix, for example, the biggest eigenvalues are going to correspond to sort of the highest degree vertices in the graph. So there'll be, so we said like a typical degree of a vertex will look like a Poisson. So there'll be some probability that it's 0, but there'll also be some probability that it's very big. So the maximum degree in the graph will be like log n over log n. And those very high degree vertices generate big eigenvalues, actually big negative eigenvalues. And so the eigenvectors associated with those will be very localized in the graph. They'll basically just be telling you, here is a high degree vertex, rather than something about the community structure. And for the random walk graph, it would fail for a different reason. Okay. On the other hand, these methods worked very well when applied to denser graphs. So some of the citations I had earlier were in sort of the denser model where say each pair gets connected with a constant probability, so the average degree is growing like n. If you have a dense graph, the degree distribution becomes much more concentrated. There's not much difference between the highest degree vertex and the lowest degree one. So the sort of inhomogeneities in the graphs become insignificant, and the community structure is really becomes the dominant feature. And so they work for dense graphs, but these particular spectral methods don't work for in the sparse setting. Okay. So we proposed the following spectral algorithm. So the matrix will now be indexed by the directed edges of the graph. So the number of rows and columns is twice the number of edges. It's not a symmetric matrix, and it looks something like so. So the directed edges are like ij and kl, and so you put a 1 essentially if j equals k and I is not equal to l. So, and we call this the non-backtracking matrix, and the reason is because it's essentially, well, if you take powers of it, you're essentially counting non-backtracking paths within the graph. So a non-backtracking path is a path of vertices connected by edges in the graph where you're not allowed to backtrack. So backtracking would mean you go from I to j and then straight back to I. So if you disallow those sorts of things, then sort of this is, I mean, that's exactly what this sort of I not equal to L condition is set. Okay. And if we said the graph locally looks like a tree, non-backtracking walks are very simple on the tree. They're basically just one paths that go straight down the tree. They're never allowed to go back up. Okay, why would you come to this as a matrix to look at? Well, if you look at the belief propagation equation, so each of these messages, the Rij's, are really vertex I telling vertex j how likely it thinks it's going to be in that it's blue, say. And so imagine none of the vertices had a very strong opinion. They're all close to a half. So it's just by symmetry, everything being, all the R's being a half would be a fixed point of this equation. So take that fixed point and linearize around it. Then you have a sort of linear map, and it's exactly this non-backtracking matrix. So it's really a linearization of belief propagation. Okay, but belief propagation is nonlinear and complicated, whereas this is now a problem in linear algebra, and you can try and analyze it. We tried to analyze it, and we're not successful. So this is a paper with physicists, and so it appears in the Proceedings of the National Academy of Science. There's no proofs in the paper. This is the only paper I've written that has no proofs in it. It's also my most highly cited paper. So there's maybe a message in that, but okay. Okay, but fortunately, other people were able to analyze this later on. So, but before I get to that, so since we don't have proofs, I'll have some simulations instead. Okay, so the x-axis is sort of this flip rate, which I guess is b over a plus b, and this is sort of the overlap, the fraction of labels that you're getting correct. So you want it to be 1, and a half would just be random chance. The cavity matrix is just a different name for this non-backtracking matrix. And you see that it tracks pretty well what belief propagation does, and we think belief propagation should be optimal. On the other hand, if you look at the random walk matrix, or another similar one was the modularity matrix, for pretty low values of the b over a plus b, they're already doing quite poorly. And in fact, actually, this was for, I guess, a network of size 100,000. If you took bigger values of n, the performance, they would drop off even more quickly here. It's didn't show, actually for any positive value of epsilon, the performance of those two matrices will tend to a half, meaning not doing better than random chance. Okay, and this is sort of the same plot, except fixing the flip rate and varying the average degree, and you see the same sort of thing. The performance of the non-backtracking matrix pretty much matches the performance of belief propagation. And in particular, they seem to hit a half at about the same point. Okay, so how do you analyze the non-backtracking matrix? Well, you can look at its eigenvalues, and they have a really interesting distribution that we don't, that there's still a lot of questions about. But for the point of view of community detection, there's really three things you want to know. So the biggest eigenvalue here at about 3, or will be at a plus b over 2. This will basically represent the average degree in the graph, or the sort of branching rate of non-backtracking walks. The second biggest eigenvalue should appear at a minus b over 2. And all of the other ones should be in a ball of radius about square root of a plus b over 2. So the bulk of the distribution is in this ball. The biggest one is out here. And the second biggest one is maybe outside here. It's out, so you can check when is a minus b over 2 out bigger than square root of a plus b over 2. It's exactly when tau is greater than 0. So this the condition is exactly the condition you need for the second eigenvalue to lie outside of the bulk. Okay, and this picture was established rigorously by Bordenave, Lalage, and Mossel-Neeman. They were, at least in the sense that they could show that there's a second eigenvalue here, or around here, that's correlated with the partition, and that all of the other eigenvalues lie inside, at least 1 plus epsilon times this radius.
The size was the number of edges, or twice the number of edges.
Yeah, so this is as the number of edges or the number of vertices is tending to infinity, yeah.
Usually when the eigenvalues that lie inside the infinity, for normal matrices.
Yeah.
Is this a normal matrix in any sense? Or?
So,
of course, there are those two exceptions, but...
yeah, so I mean, if you take like a random matrix with just IID entries, then the circular law will say that they'll all be in some circle. But also it will say that you have the uniform distribution of the sort of the point process will be like the uniform measure. Here, the point process really doesn't look like the uniform. So that's and there's no results on what it looks like here. There's also, I mean, you can't see it from this picture, but there's also a lot of eigenvalues at 0, 1, and -1 as well. So, but it looks like there's some extra structure happening around here, and we don't understand that. I'm not an expert on random matrices either, but one of the usual problems with proving things about random matrices is you want to show that the smallest singular value of the matrix isn't too small, and I think for the stochastic block model, I don't really know how to do that sort of thing. Maybe that's a question for a nearby. But okay, so so then this is just a plot of how if you look at the first, second, up to fifth eigenvalues, how they correlate with the true partition. So the pluses indicate the performance of belief propagation. The blue stars here are the second eigenvector, and all the other ones are essentially uncorrelated with it, which is what we expect. Okay, and so of course then you can try and apply this to real data, and so there are in the community detection world there are certain sort of data sets. One, maybe the most famous, is there's a karate club, which was, I mean, literally a karate club, and at some point there's some dispute, and that it's like they split into two groups, and some sociologists had studied this and looked at the network connections beforehand. So the question is sort of, given that graph, can you predict who's in which? Can you predict the split that's about to emerge? And then there are other ones of, like, you look at which political blogs sort of link to each other. That gives you another network. So the non-backtracking matrix, in some of these examples, it does the best. In most of them, it does quite well. So let me tell you about some sort of, so this is all kind of old, and so let me tell you about some more developments. Or, no, actually, one other question you can ask is, I've just been talking about getting like a half plus epsilon recovery rate, or doing something slightly better than random chance. And I guess I didn't say that there are sort of trivial reasons why you can't hope to, in the sparse case, get really the exact partition. The most trivial reason is that there are some people who have no friends in this model. There'll be a constant fraction with degree 0, and of course you won't be able to distinguish which ones are blue and which ones are red of those. But even within the ones that do have a reasonable number of connections, there'll be some people who are just happen to have more friends in the other community than their own. So you can't hope to get everyone right unless you let A and B vary with n. If you want the fraction correct to tend to 1, you need that A minus B squared over A plus B, the sort of signal to noise ratio tends to infinity. If you want to get absolutely everyone correct, you need this condition in terms of, so it's in terms of the probability that one binomial random variable is bigger than another. Okay, so what does this condition mean? It's basically saying that you want that for every person, they have more friends in their own community than in the other community. You can imagine if that wasn't the case, if there were people with more friends in the opposite community, you wouldn't be able to tell who they are, and so you couldn't really hope to get everyone right. But the converse is also true. If everyone has more friends in their community than the other community, then there's algorithm that with high probability will get everyone right. And basically what you do is you start off with a sort of an algorithm that does well, it gets almost everyone right. And then you look for people who in this reconstruction have more friends in the other community than their own, and you sort of fix them up locally. And you can show that this sort of a good start with, and then with sort of locally repairing will work. And when you have this, when this probability tends to 0, then you'll be able to correctly guess all of the communities with high probability. Okay. So then in terms of sort of more recent developments, Abe and Sandon sort of generalized these results to sort of more general stochastic block models. So you have, rather than having 2 blocks, you can have any fixed number of blocks, and the connection probability between each block can be whatever you want. So essentially you would have a matrix that says between block I and block J, you have probability Qij over n of adding an edge between them. And they showed that, so you take whenever tau is greater than 1, that the analog of the Keston-Stigum bound holds, then you can efficiently sort of at least approximately recover some network structure. But they also showed that when you have more blocks, when you have at least 5 or more blocks, you can also you can reconstruct things even when you're slightly below tau equals 1. So it's not the right prediction when you have more blocks. But this algorithm is one that's based on brute force. It's not an efficient algorithm. It's related to understanding the Potts model on sort of a generalization of the Ising model to more states on infinite branching process trees. And essentially the question of when the free Potts measure is extremal. So the Keston-Stigum bound says that whenever tau is greater than 1, it's not extremal. But when you have 5 or more states, even for slightly smaller values of tau, it will still not be extremal. And then sort of the most recent work in this area that I want to highlight is Kojoglán, Kožákla, Perkins, and Zed-Radova. So Kožákla and Zed-Radova are some of the physicists who had the original conjecture, but this is a paper with proofs. And they looked at sort of what you might call the antiferromagnetic or sometimes disassortative stochastic block model, which means you're more likely to be friends with people in the other community than within your own. And in this case, they can use techniques coming from the theory of spin glasses, things like the sort of ideas developed for the Sharrington-Kirkpatrick spin glass model, to give a variational formula for the sort of information theoretic threshold in these models, the point at which you can, with infinite computing resources, do community detection. So one very natural question is, so they have a variational formula. It's not necessarily one that's that easy to analyze, but you can ask for the 3-state model, is it the case that the threshold corresponds to tau equals 1? So it's expected that the 3-state Potts, the threshold for extremality of the 3-state Potts model on the infinite tree corresponds to tau equals 1. And so that would sort of predict that this should be the right threshold. But that's I think an interesting open problem. 4 is really sort of the critical number of blocks, and there things can be more difficult. It's sort of, and it might be that you get different behavior depending on what the average degree is or not. Okay, well, thanks for listening.
Questions? Can I ask one question? So what is expected to happen as you let the number of clusters go to infinity? Slower rate than the size?
So in a sense, it should get further and further away from the tau equals 1 case. Yeah, it will go to 0. Yeah. So I mean, one sort of, so in the sort of antiferromagnetic setting, where A is less than B, you can, setting A as 0 means you're not connected to anyone in your own group. And that's basically the same as saying you have a proper coloring of the graph with, you have if you have Q states, then you're looking for Q colorings of the graph. And so the model then is sort of essentially you take your graph, or you take your set of vertices, you color the vertices, and then you look for a graph conditional on that being a proper coloring of the graph. Coloring meaning sort of in the graph coloring sense of neighboring vertices having to have different colors. And for that, there are sort of like you can already say pretty well what the about where the sort of information theoretic threshold will be, and it will be sort of so the relationship will sort of be if so if D is the average degree and Q is the number of colors, then it should be D is like 2Q log Q. If whereas the second eigenvalue or the Kestenstigen bound would be something like the degree is like Q minus 1 squared, or so you have a so it will be quite a big difference, and you'll certainly have tau going to 0. The number of communities, yeah. Yeah.
Thanks. So in some large Q limit, are there any simplifications? If you scale Q still such that n by Q is still Q by n is going to
so there are predictions for what should happen, and so sort of it's closely related to the understanding of colorings on random graphs, which is a sort of one of the other things these people and me as well are interested in is sort of random constraint satisfaction problems, and sort of finding a coloring of a graph is sort of one of the sort of classic examples of that. And so it should, giving sort of the right asymptotics is sort of essentially known. You should be able to also get that from the variational formula. Now, if the number of colors is growing at some fast rate, then I'm not sure exactly about what.
Maybe a Q by n held fixed. Maybe I don't know whether that's.
Okay, so if okay, but the bigger you make Q, also you need to. Okay, well, okay. If you're letting Q grow, you also have to let the average degree grow, and so soon you'll start dealing with sort of non-sparse graphs. And that's sort of and that may simplify things, because when the graph isn't sparse, or is denser, quantities are more concentrated, and they can be easier to analyze. Yeah, but I haven't specifically thought about that.
If not, let's thank Allan again.